January 5, 1943, North Atlantic, 200 miles west of the Hebrides. The British destroyer HMS Scylla pitches through 12-foot swells, her crew at action stations as radar operators track a formation of German Focke-Wulf Condor bombers approaching from the northeast. In the ship's forward gun director, Lieutenant Commander James Whitley watches the contacts close, knowing his 5-inch guns carry something the enemy has never encountered. Each shell loaded into the breech contains a miniaturized radio transmitter smaller than a milk bottle, packed with 130 electronic components designed to survive forces that would pulverize conventional machinery. The shells are marked with cryptic designations that mean nothing to German intelligence but everything to the men who will soon witness their effect. What happens in the next 18 minutes will demonstrate why the Luftwaffe's bomber formations, once the scourge of Atlantic convoys, are about to face a technological revolution that will render their tactical doctrine obsolete. The electronic brain inside each shell is waiting, silent and patient, for the moment when mathematics and physics converge to create destruction at a distance that conventional weapons could never achieve. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The proximity fuse represented the culmination of a desperate race that began in the summer of 1940, when Britain stood alone against the combined might of the German Luftwaffe. The battle for Atlantic shipping lanes was reaching its critical phase, with German bombers and reconnaissance aircraft directing U-boat wolf packs to merchant convoys with devastating effectiveness. British anti-aircraft defences, still relying on mechanical time fuses that required gunners to estimate range, altitude, and speed, before manually setting each shell's detonation time, were proving inadequate against fast-moving aircraft that could alter course and altitude at will. The mathematics were brutal and unforgiving. A conventional 5-inch anti-aircraft shell with a mechanical time fuse had to explode within 20 feet of a target to inflict lethal damage. This required the gun crew to predict exactly where the aircraft would be several seconds in the future, calculate the precise flight time of the shell, manually set the fuse to detonate at that exact moment, and hope the pilot didn't change course after the gun fired. Studies conducted by the Royal Navy in 1940 indicated that destroyers required an average of 2,500 rounds of 5-inch ammunition to destroy a single enemy aircraft using conventional time fuses. At that rate of expenditure, the average destroyer would exhaust its entire anti-aircraft ammunition supply after destroying just 2 aircraft, assuming perfect conditions and no mechanical failures. The British had conceived the basic principle of what they called the proximity fuse in 1940, when scientists at the Telecommunications Research Establishment recognized that a miniature radio transmitter could theoretically measure its distance from a target by analyzing the Doppler shift of reflected radio waves. The concept was elegantly simple in theory, but seemed impossible to execute in practice. The fuse would need to contain a radio transmitter, a receiver, amplification circuits, a power source, and a detonation mechanism, all miniaturized to fit inside the nose of a 5-inch shell. More critically, every component would have to survive the instant of firing, when the shell experienced acceleration forces exceeding 20,000 times the force of gravity. Conventional radio tubes, even the smallest available, would shatter instantly under such stress. The glass envelopes that contained the vacuum would fragment into powder, the filaments would snap like spider webs hit by hammers, and the delicate internal structures would collapse into twisted wreckage. British scientists, already overwhelmed with radar development and other critical military projects, concluded that creating a proximity fuse capable of surviving gun launch was theoretically possible, but practically impossible given their limited resources and manufacturing capacity. The problem crossed the Atlantic in September 1940, carried by the Tizard mission, perhaps the most significant technology transfer in military history. Sir Henry Tizard, leading a small group of British scientists, travelled to the United States, carrying Britain's most closely guarded technological secrets, including cavity magnetron designs that would revolutionize radar and the theoretical groundwork for the proximity fuse. The British proposition was straightforward and desperate. They would share everything they knew if American scientists and industry could. and transform theory into mass-produced reality. The United States, still officially neutral but increasingly aware of the German threat, accepted the challenge with characteristic ambition. The National Defense Research Committee assigned the Proximity Fuze project to Section T of the Applied Physics Laboratory at Johns Hopkins University, placing it under the direction of Dr. Merle Tuve, a brilliant physicist who understood both the theoretical principles and the practical engineering required to make the impossible device work. Tuve assembled a team that combined academic researchers with practical engineers from American industry, creating a collaborative environment that would become the model for subsequent wartime technology programs. The challenges they faced would have discouraged less determined men. The proximity fuse needed to survive not just the instant of firing, but the entire flight to the target. The shell would spin at 25,000 revolutions per minute as it traveled through the gun's rifling, creating centrifugal forces that would tear apart conventional electronic components. The shell would experience temperature variations from 100 degrees Fahrenheit to -50 degrees as it climbed through different atmospheric layers. The radio system needed to function in an environment of extreme vibration, electromagnetic interference from the gun's electrical firing system, and the physical shock of air resistance at speeds exceeding 2,600 feet per second. Most critically, all of this had to be achieved using vacuum tube technology, the only electronic amplification method available in 1940. The vacuum tube problem seemed insurmountable until engineers at Sylvania and Raytheon developed specialized miniature tubes with reinforced internal structures and glass envelopes made from special formulations that could flex slightly under stress without shattering. These tubes, designated as the WWII series, were unlike anything manufactured before. The filaments were wound from special alloys that could withstand tremendous shock. The glass was formulated to maintain structural integrity under forces that would pulverize normal glass. The internal elements were designed with redundancy, so that even if some structures failed during launch, enough would survive to maintain functionality. Each tube was individually tested by dropping it from heights that simulated gun launch forces, with only those specimens that survived multiple drops being approved for fuse production. The manufacturing tolerances were measured in thousandths of an inch, requiring precision that pushed American industry to develop new quality control methods. The power supply presented its own series of apparently impossible requirements. The fuse needed electricity to operate its radio transmitter and receiver, but conventional batteries would be destroyed by the acceleration of firing. The solution was elegant in its simplicity but devilishly difficult to manufacture. Engineers developed a special battery that remained inert during storage but activated instantly when subjected to the acceleration forces of gun launch. The battery used a liquid electrolyte that was held in a separate chamber by a thin membrane. When the shell fired, the acceleration forced the electrolyte through the membrane into contact with the battery plates, activating the power supply at the exact moment it was needed. This battery had to remain stable for months in storage across a wide range of temperatures, then activate perfectly in the fraction of a second during gun launch, providing steady power for the 30 to 40 seconds of shell flight. The development required hundreds of iterations and the creation of entirely new manufacturing processes. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The radio frequency selection required careful calculation to balance multiple competing requirements. The Fuze's transmitter needed to operate at a frequency high enough to provide accurate range measurement, but low enough to allow miniaturized antenna designs. The chosen frequency had to avoid interference from friendly radar systems while remaining effective against the metal structures of enemy aircraft. Engineers settled on a frequency in the low VHF range, around 185 MHz, which provided good reflection from aircraft while allowing antenna designs that could be integrated into the shell's nose cone. The transmitter broadcast a continuous wave signal, with the receiver constantly monitoring the reflected energy. As the shell approached a target, the Doppler shift in the reflected frequency would change in a predictable pattern, and when this shift reached a predetermined threshold indicating lethal proximity, the fuse would trigger the shell's main explosive. Charge. The detonation mechanism itself required fail-safe designs that would prevent premature explosions while ensuring reliable detonation when required. Engineers developed a multiple safety system that kept the fuse inactive until several conditions were met in sequence. The fuse remained mechanically locked until the shell left the gun barrel and travelled at least 300 yards, preventing accidents during loading or if a gun misfired. The electrical system remained inactive until the battery activated under acceleration forces that could only occur during proper firing. The radio receiver included threshold circuits that required sustained signal patterns consistent with approaching a large metal object, not just momentary reflections from birds, raindrops, or sea spray. Only when all these safety conditions were satisfied would the fuse arm itself and begin monitoring for targets. This multiple redundancy approach proved remarkably reliable, with premature detonations occurring in fewer than 1 in 10,000 rounds. The manufacturing challenge scaled beyond anything American industry had attempted with electronic devices. The proximity fuse contained approximately 130 separate components, each requiring precision assembly under conditions that prevented contamination, moisture intrusion, or mechanical stress. The assembly process involved over 50 discrete steps, from winding the miniature coils to evacuating air from the vacuum tubes to sealing the final assembly in waterproof compounds. Each fuse required individual testing to verify that all components functioned correctly and that the radio frequency calibration fell within acceptable parameters. The testing process itself became an industrial challenge, requiring the development of automated equipment that could verify fuse functionality without the time-consuming individual testing that would have made mass production impossible. Engineers at the Applied Physics Laboratory developed test fixtures that could check multiple fuses simultaneously, using radio frequency generators to simulate target approaches and verify that each fuse would detonate at the correct distance. The security surrounding the proximity fuse program rivaled that of the atomic bomb project. Military planners recognized that if the Germans captured an intact fuse and reverse-engineered its secrets, they could develop their own versions or create countermeasures that would negate the Allied advantage. The fuses were classified at the highest level, with their existence known only to those directly involved in development, production, or tactical deployment. Shells containing proximity fuses were marked with innocuous codes that revealed nothing about their capabilities. Gun crews were trained to recognize the markings but were told nothing about how the fuses worked, only that they should fire these special shells at aircraft and expect improved results. Ships carrying proximity-fused ammunition were ordered to use them only over water, where dud shells would sink into the ocean rather than fall on land where German forces might recover them. This restriction meant that proximity fuses saw their first combat use in naval engagements rather than land-based anti-aircraft defense. The first combat test came in January 1943, when the cruiser USS Helena fired proximity-fused shells at Japanese aircraft during the Guadalcanal campaign. The results exceeded even optimistic predictions. Helena's gun crews destroyed a Japanese dive bomber with the second salvo of 3 shells, with the proximity fuse detonating the lethal shell within 70 feet of the target. The bomber disintegrated in mid-air, torn apart by shell fragments that conventional time fuses would have missed completely. The gun crews, unaware of the fuse technology they were using, reported that the new ammunition seemed uncannily accurate, as if the shells could sense their targets. Word spread quickly through the fleet that special shells were available that dramatically improved hit probabilities. Demand for proximity-fused ammunition increased faster than production could initially supply, leading to allocation systems that prioritized ships most likely to face air attack. The mathematical superiority of proximity fuses became apparent as combat data accumulated through 1943. Statistical analysis conducted by the Navy's Operations Research Group indicated that proximity-fused shells required an average of 310 rounds to destroy an aircraft, compared to 1,162 rounds for conventional time-fused shells. This nearly 4-fold improvement in effectiveness meant that a destroyer's anti-aircraft battery could engage 4 times as many targets with the same ammunition expenditure, or achieve the same defensive effectiveness with 1/4 the ammunition. The implications for naval logistics were profound. Ships could carry effective anti-aircraft defenses for longer patrols without requiring frequent ammunition replenishment. The weight saved by requiring fewer shells could be allocated to other weapons or supplies. Most critically, the improved effectiveness meant that formations of bombers that would have overwhelmed conventional defenses could now be engaged with realistic hope of success. The proximity fuze's impact on Luftwaffe bomber tactics would become fully apparent in the European theatre, where German aircraft faced the same technological surprise that had devastated Japanese aviation. The Focke-Wulf Condor, a 4-engine maritime patrol bomber that had terrorized Atlantic convoys in 1940 and 1941, relied on tactics developed when British anti-aircraft fire was relatively ineffective. Condor pilots approached at medium altitude, around 8,000 feet, where they could maintain stable bombing platforms while remaining above the effective range of lighter anti-aircraft weapons. The aircraft's robust construction allowed it to survive near misses from conventional shells, and its experienced crews had learned to watch for the black puffs of exploding time-fused shells and adjust course to avoid the predicted positions. These tactics, refined through 2 years of operations, assumed that British defensive fire would continue to follow predictable patterns. The introduction of proximity fuses invalidated every assumption that German bomber tactics had been built upon. Luftwaffe crews, accustomed to seeing anti-aircraft bursts in predictable locations, suddenly faced shells that exploded with impossible accuracy at exactly the right altitude and position to inflict maximum damage. The distinctive black puffs of conventional anti-aircraft fire were replaced by explosions that seemed to track aircraft movements, detonating at positions that suggested the British had developed some form of guided ammunition or predictive fire control, far beyond what German intelligence believed possible. Condor crews reported shells exploding directly in their flight paths with such consistency that they suspected new radar-directed fire control systems had been deployed. The truth, that each shell carried its own electronic brain capable of sensing proximity to metal objects, was beyond what German tactical doctrine had prepared them to encounter. The 4-engine bombers, previously confident in their ability to survive British anti-aircraft fire through a combination of altitude and evasive manoeuvring, suddenly faced defensive systems that turned near misses into lethal hits. The transformation of Luftwaffe bomber formations from confident attackers to vulnerable targets happened with shocking speed once proximity-fused ammunition reached operational deployment in meaningful quantities. By the spring of 1943, British destroyers and cruisers operating in the North Atlantic and Mediterranean theatres carried increasing percentages of proximity-fused 5-inch ammunition, with allocation rising from 15% of anti-aircraft loads in early 1943 to over 50% by the autumn of that year. German bomber crews, particularly those flying the Heinkel He 111 and Junkers Ju 88 medium bombers that formed the backbone of Luftwaffe maritime strike capabilities, began reporting catastrophic losses during attacks on Allied convoys. Formations that had previously accepted losses of 5 to 10% per mission suddenly experienced casualty rates approaching 30%, levels that made sustained operations impossible. Luftwaffe intelligence officers, analysing damage reports from surviving aircraft and interrogating captured British sailors, struggled to understand what had changed in Allied defensive capabilities. The Heinkel He 111, a twin-engine bomber that had served since the Spanish Civil War and remained in production. Throughout the war, despite its obsolescent design, proved particularly vulnerable to proximity-fused anti-aircraft fire. The aircraft's relatively slow maximum speed of 270 miles per hour and its large cross-section made it an ideal target for shells that could sense proximity to metal structures. He 111 formations approaching Allied convoys in the Mediterranean had developed tactics that involved approaching at wave-top height to avoid radar detection, then climbing to medium altitude for their bombing runs. This profile, effective against conventional time-fused anti-aircraft fire that required precise altitude estimation, became a death sentence once proximity fuzzes entered service. The climbing phase of the attack, when aircraft were most vulnerable because they were gaining altitude at predictable rates, now exposed bombers to shells that automatically detonated at optimal burst heights. German crews reported seeing shells explode in perfectly timed patterns that created walls of shrapnel through which their formations had to fly, with no apparent way to predict or avoid the lethal zones. The tactical adjustments attempted by Luftwaffe commanders demonstrated both their desperation and their lack of understanding about what they faced. Some units tried approaching at extremely low altitude, hoping to fly beneath the effective range of ship-mounted anti-aircraft guns. This tactic proved counterproductive because proximity phases worked equally well at low altitude, detonating when shells passed close to the sea surface and creating horizontal patterns of fragments that were actually more effective against low-flying aircraft than conventional shells would have been. Other units attempted high-altitude approaches above 10,000 feet, reasoning that the thinner air and greater distances would reduce anti-aircraft effectiveness. The proximity fuses, calibrated to detect metal objects at any altitude within their operational envelope, simply detonated at higher altitudes with undiminished lethality. The most sophisticated Luftwaffe tactic involved splitting formations and attacking from multiple directions simultaneously, hoping to overwhelm defensive fire through sheer numbers of targets. This approach occasionally succeeded in landing some bombers on target, but the casualty rates remained unsustainable, even when attacks achieved partial success. The Focke-Wulf 200 Condor, Germany's premier maritime patrol bomber, suffered disproportionately from proximity fuse technology because its operational profile placed it directly in the engagement envelope where the fuses proved most effective. Condor missions typically involved long-range patrols at medium altitude, searching for convoys that could then be attacked directly or reported to U-boat wolf packs for coordinated strikes. The aircraft's 4 BMW engines gave it the range to patrol far into the Atlantic, but its size and relatively ponderous handling made it vulnerable once engaged by determined defences. Condor crews had grown accustomed to British anti-aircraft fire as a hazard to be respected but not feared, something that could be evaded through altitude changes and course adjustments once the distinctive black puffs of exploding shells indicated where British gunners thought the aircraft would be. The introduction of proximity fuses transformed this calculable risk into something approaching certain death. Condors approaching within range of convoy escorts suddenly faced shells that exploded not where gunners predicted they would be, but where they actually were, eliminating the advantage that experienced pilots had gained through learning to read conventional anti-aircraft patterns. The destruction of Focke-Wulf Condors accelerated dramatically through 1943 and into 1944 as proximity fuse production expanded and more Allied warships carried the technology. British Admiralty records document a steady increase in Condor losses, with dozens of the valuable long-range bombers shot down over the Atlantic during this period. Each loss represented not just an aircraft, which German industry struggled to replace, but 4 trained crew members whose experience could not be replicated. The Condor Force, which had numbered over 60 operational aircraft in early 1941, dwindled to barely 20 serviceable machines by mid-1944, victims of attrition that proximity-fused anti-aircraft fire accelerated beyond sustainable levels. Luftwaffe commanders, recognizing the Condor's increasing vulnerability, began withdrawing the type from frontline maritime patrol duties, replacing them with smaller, faster aircraft that at least had some hope of evading the mysteriously accurate British anti-aircraft fire. The Junkers Ju-88, perhaps the most versatile aircraft in the Luftwaffe inventory, serving as bomber, dive bomber, night fighter, and reconnaissance platform, encountered proximity fuzzies across every theatre where it operated. Ju-88 units attacking Allied shipping in the Mediterranean, striking at invasion beaches in Normandy, and conducting anti-shipping operations in the North Sea all reported the same phenomenon. British and American anti-aircraft fire had become devastatingly more effective, with shells exploding at precisely the right positions to inflict maximum damage. The Ju-88's relatively high speed and good maneuverability provided some protection, allowing skilled pilots to occasionally evade the worst of the defensive fire, but formation flying, essential for effective bombing attacks, left aircraft exposed to the coordinated anti-aircraft fire that proximity fuzzes made practical. German tactics had traditionally relied on tight formations for mutual defensive fire from onboard machine guns, but these formations became collective targets for Allied gunners, who could now engage multiple aircraft with shells that automatically detonated at optimal positions within bomber boxes. The psychological impact on Luftwaffe bomber crews paralleled the experience of Japanese kamikaze pilots facing similar technology in the Pacific. German aircrew, trained to understand aircraft performance, ballistics, and tactical doctrine, found themselves confronting defensive systems that seemed to operate by principles they couldn't comprehend. Debriefing reports from surviving missions included descriptions of shells that appeared to follow aircraft through evasive maneuvers, explosions that occurred at impossible positions suggesting some form of guided ammunition and anti-aircraft fire that was effective at ranges and altitudes where conventional weapons should have been useless. Luftwaffe intelligence officers, analyzing these reports alongside physical evidence from damaged aircraft that returned to base, documented shell fragment patterns that suggested bursts were occurring closer to aircraft than conventional time fuses could achieve. Some intelligence analysts correctly hypothesized that the Allies had developed some form of proximity sensing mechanism, but the technical details and the sheer scale of deployment remained mysteries. The German attempt to develop their own proximity fuse technology illustrated the disparity in industrial and scientific capabilities between the Third Reich and the Allied powers. German scientists understood the theoretical principles involved and had conducted preliminary research into radio-based proximity sensing as early as 1939. However, the vacuum tube technology required for miniaturization proved beyond German manufacturing capabilities under wartime conditions. The German electronics industry, already strained by competing demands for radar equipment, communications gear, and increasingly sophisticated night fighter systems, lacked the spare capacity to develop and mass-produce proximity fuses. More fundamentally, the precision manufacturing and quality control required for proximity fuse production demanded industrial practices that German war economy had never fully developed. The same organizational and technical factors that had allowed American industry to produce 22 million proximity fuses by war's end simply did not exist in Germany, where chronic material shortages, transportation disruptions from Allied bombing, and fragmented command structures prevented the kind of coordinated industrial mobilization that proximity fuse production required. The German Kriegsmarine, desperate for improved anti-aircraft defenses as Allied air superiority became overwhelming, attempted to develop indigenous proximity fuse technology through several parallel programs. The most advanced German effort, designated as Project Kranich, aimed to create a proximity fuse based on acoustic rather than radio principles, reasoning that sound waves might be easier to miniaturize than radio transmitters. Prototype Kranich fuses used small microphones to detect the distinctive sound signature of aircraft engines, triggering detonation when sound intensity reached predetermined levels. Testing revealed fundamental problems that German engineers never solved. The acoustic fuses proved unreliable in the noisy environment of naval combat, often detonating prematurely from the sound of the firing ship's own engines or failing to detect aircraft against background wind noise. More critically, the acoustic approach could not provide the precise range discrimination that radio-based proximity fuses achieved, resulting in burst patterns that were only marginally more effective than conventional time fuses. Project Kranich was eventually abandoned in late 1944 after consuming resources that might have been better spent on other defensive systems. The strategic bombing campaign over Germany provided another demonstration of proximity fuse effectiveness, though in a different tactical context than maritime operations. American heavy bombers, particularly the Boeing B-17 Flying Fortress and consolidated B-24 Liberator, faced devastating attacks from Luftwaffe fighters during daylight raids over German industrial targets. The standard German tactic involved head-on attacks by fighters equipped with heavy cannon, engaging bomber formations before they reached their targets, and again during egress. Allied escort fighters provided some protection, but gaps in coverage allowed German interceptors to inflict serious losses during certain phases of bombing missions. The introduction of proximity-fused ammunition for bomber defensive armament in late 1943 changed this equation significantly. American bombers began carrying limited quantities of proximity-fused rounds for their 50 caliber machine gun turrets, though the smaller caliber meant that these fuzzies operated on slightly different principles than the naval 5-inch versions. The effectiveness of proximity fuses in aerial combat, where both the firing platform and target were moving at high speeds, demonstrated the sophistication of the fuse design. The radio proximity fuse had to distinguish between closing velocities that indicated an approaching enemy fighter versus diverging velocities from aircraft that had already passed. The Doppler shift calculations became more complex when both platforms were moving, requiring fuse circuits that could process relative motion in 3 dimensions while compensating for the bomber's own speed and direction. American engineers solved these problems through careful calibration of the fuse's detection thresholds and response times, creating devices that would arm only when specific velocity and approach angle conditions were met. The result was defensive fire that no longer required precise aim to be effective. Bomber gunners who scored direct hits only occasionally with conventional ammunition found that proximity-fused rounds dramatically improved their hit probabilities, particularly against fighters in high-speed attack runs, where conventional aiming techniques struggled to predict future positions accurately. Luftwaffe fighter pilots, already facing increasingly dangerous odds as American fighter escorts gained numerical superiority and operational experience, found their tactical doctrine undermined by proximity-fused defensive fire from bomber formations. The head-on attack, which had been effective because it presented the smallest target profile to bomber gunners and maximized closure rates that made accurate defensive fire difficult, became significantly more dangerous when bomber turrets were loaded with ammunition that didn't require direct hits. German pilots reported shells exploding near their aircraft with disturbing consistency, even when they were certain bomber gunners hadn't achieved proper lead angles. The psychological impact was significant. Fighter pilots, who relied on aggression and precision flying to press attacks through defensive fire, found themselves flinching from encounters that seemed to involve defensive systems operating on principles beyond their understanding or ability to counter. Luftwaffe fighter losses, already unsustainable due to overall Allied air superiority, increased further as proximity-fused defensive fire made the bomber stream an even more dangerous environment. The Battle of the Atlantic, which Winston Churchill later identified as the only campaign that truly frightened him during the entire war, saw proximity fuses contribute to the decisive defeat of the U-boat threat by making Luftwaffe maritime patrol bombers ineffective. The German strategy in the Atlantic had always relied on cooperation between submarines and aircraft, with long-range bombers like the Condor providing reconnaissance that allowed U-boat wolf packs to concentrate against convoys. The systematic destruction of Luftwaffe maritime patrol aircraft by proximity-fused anti-aircraft fire disrupted this cooperation, forcing U-boats to rely on their own limited sensors to locate targets. The intelligence advantage that maritime air patrol had provided to German submarine operations disappeared as Condor losses mounted, and surviving aircraft were forced to operate at greater distances from Allied convoys, where their reconnaissance effectiveness was reduced. British and American naval commanders noted the correlation between increasing proximity, fuse deployment, and decreasing U-boat effectiveness, recognizing that the electronic shell had helped win the Atlantic battle by denying Germany the air reconnaissance that submarine warfare required. The Normandy invasion in June 1944 provided perhaps the most dramatic demonstration of proximity fuse effectiveness against Luftwaffe bomber formations. German commanders, recognizing that the invasion beaches represented an existential threat to the Third Reich, committed remaining bomber forces to desperate night attacks against the Allied landing fleet. Luftwaffe bomber units, including surviving He-111 and Ju-88 squadrons, attempted to strike at the massive concentration of ships anchored off the French coast. The attacks failed catastrophically, with German bombers shot down in dozens by anti-aircraft fire from hundreds of Allied warships, most carrying proximity-fused ammunition. The night attacks, which German planners had hoped would reduce visibility enough to give bombers some advantage, proved equally futile, because proximity fuses required only that shells pass close to targets, not that gunners see their targets clearly. Allied radar directed guns toward approximate bearing and elevation of incoming aircraft, and proximity fuses ensured that shells passing anywhere near those positions would detonate effectively. The mathematical reality of proximity fuse effectiveness became overwhelming when, multiplied across the scale of operations in 1944 and 1945, every Luftwaffe bomber formation that approached Allied naval forces faced defensive fire that was 3 to 4 times more effective than what German tactical doctrine had prepared them to encounter. Formations that might have survived attacks with 20% losses using conventional defenses now faced destruction rates approaching 40 or 50%. These casualty levels made sustained bomber operations impossible, forcing the Luftwaffe to abandon maritime strike capabilities and reduce bomber operations generally to levels that could not meaningfully affect Allied operations. The destruction of German bomber forces through attrition, accelerated by proximity fuse technology, contributed to Allied air superiority that became absolute by late 1944. The Luftwaffe, which had begun the war as perhaps the world's most effective tactical air force, ended it as a broken force, unable to defend German cities or contest Allied control of European skies, defeated partly by technology that transformed defensive fire from an acceptable hazard into a prohibitive barrier. The industrial mobilization required to produce proximity fuses at the scale necessary to achieve strategic impact represented one of the war's most remarkable organizational achievements, rivaling even the Manhattan Project in complexity and exceeding it in the sheer number of precision components manufactured. By the end of 1944, American factories were producing proximity phases at a rate exceeding 70,000 units per day, a production tempo that required coordination across 112 companies operating more than 200 individual factories scattered across the United States. The Crosley Corporation, better known before the war for manufacturing radios and refrigerators, transformed its Cincinnati facilities into the world's largest proximity fuse production center, employing over 10,000 workers operating continuous shifts 7 days per week. Each worker became a specialist in 1 or 2 manufacturing steps, performing the same precise operations hundreds of times per day with tolerances measured in thousandths of an inch. The production lines achieved efficiency levels that would have seemed impossible in peacetime, with completed fuses rolling off assembly lines at rates approaching 1 unit every 6 seconds during peak production periods. The quality control systems developed for proximity fuse manufacturing established standards that would influence American industrial practice for decades after the war. Every fuse underwent multiple testing stages, beginning with component-level verification of individual vacuum tubes, resistors, capacitors, and mechanical elements before assembly. Completed fuzzes faced functional testing that simulated the radio frequency environment they would encounter during actual use, with automated test equipment checking that each unit's transmitter operated at the correct frequency and that the receiver circuits triggered detonation at appropriate signal thresholds. Statistical sampling protocols ensured that defective batches could be identified and removed before they reached operational units, preventing the catastrophic scenario where defective ammunition might fail at critical moments. The rejection rate for proximity fuses, initially as high as 15% during early production in 1942, dropped below 2% by 1944 as manufacturing processes matured and workers gained experience. This level of quality control, applied to millions of units containing sophisticated electronics, represented manufacturing achievement that demonstrated American industrial capabilities at their apex. The cost of proximity fuse development and production, while substantial by any measure, proved remarkably economical when measured against the military value they provided. The entire proximity fuse program, including research, development, factory construction, and production of over 22 million units, cost approximately $1 billion in 1940s currency. This investment, spread across 4 years of war, represented less than 0.5% of total American war expenditure. The cost per Fuze, initially over $700 for early prototype units in 1941, dropped to just $18 by 1945 through manufacturing efficiencies and economies of scale. At $18 per unit, a proximity Fuze cost roughly the same as 3 gallons of high-octane aviation fuel or 20 pounds of aluminum, negligible expenses compared to the value of the ships and aircraft they protected. Naval commanders calculated that a single destroyer saved from sinking by proximity-fused anti-aircraft fire represented a return on investment of over 100,000 to 1, considering that the ship cost millions to construct and carried hundreds of trained sailors whose replacement was impossible. The Allied strategic advantage created by proximity fuzzes extended beyond the immediate tactical effectiveness against bomber formations to influence German military planning and resource allocation in ways that compounded the technology's impact. Luftwaffe commanders, confronting casualties they could not sustain, were forced to withdraw bomber units from maritime operations and redeploy them to other theatres where they might face less devastating defensive fire. This redeployment disrupted German plans for coordinated air-sea operations against Allied shipping and forced submarines to operate without the air reconnaissance they had relied upon. The German Navy, desperate to provide its ships with anti-aircraft defences comparable to what Allied vessels possessed, diverted resources from other weapon programs into futile attempts to develop indigenous proximity Fuze technology. These misdirected efforts consumed engineering talent and manufacturing capacity that might have produced more conventional weapons systems, illustrating how technological superiority could force opponents into wasteful programs chasing capabilities they lacked the industrial base to achieve. The strategic bombing campaign over Germany demonstrated proximity Fuze effectiveness in the most challenging possible environment, where German defences were most concentrated, and Luftwaffe fighter opposition remained formidable despite overall Allied air superiority. American bomber formations penetrating deep into German territory during daylight raids faced coordinated attacks from fighter groups equipped with cannon and rockets specifically designed for bomber destruction. The introduction of proximity-fused defensive ammunition for bomber turrets in late 1943 and early 1944 gave American gunners capabilities that German fighter tactics had not anticipated. The standard Luftwaffe attack profile involved high-speed passes from angles calculated to minimize exposure to defensive fire, with fighters breaking away immediately after firing to avoid prolonged engagement. Proximity-fused ammunition disrupted these tactics by expanding the lethal envelope around bombers, making breakaway maneuvers more dangerous because shells that missed during the attack run might still detonate lethally during the fighter's departure. German pilots reported increasing difficulty in pressing attacks home, with defensive fire seeming to follow them even after they had supposedly cleared the danger zone. The Luftwaffe's response to proximity-fused bomber defences illustrated both the adaptability and ultimately the futility of tactical adjustments against fundamental technological disadvantages. Fighter units experimented with standoff attacks using heavy rockets fired from beyond the range of bomber defensive guns, but these tactics proved inaccurate and consumed expensive rockets at rates that German industry could not sustain. Other units tried coordinated attacks from multiple directions simultaneously, hoping that bombers could not effectively defend against threats from all angles at once. These tactics occasionally succeeded, but required levels of coordination and timing that became impossible to maintain, as experienced fighter leaders were lost and replacement pilots arrived with minimal training. The most desperate German tactic involved ramming attacks by fighters stripped of weapons to increase speed, with pilots ordered to bail out after destroying their targets through collision. These Sonderkommando Elbe missions, flown in April 1945, achieved minimal success at catastrophic cost, with most attacking fighters shot down by proximity-fused defensive fire before reaching ramming distance. The failure of these desperate measures demonstrated conclusively that no amount of courage or tactical innovation could overcome the fundamental advantage that proximity fuses provided to American bomber defenses. The Mediterranean theater provided particularly clear evidence of proximity Fuze impact because the confined waters and shorter distances allowed detailed tracking of Luftwaffe bomber losses and their correlation with introduction of new defensive technologies. German bomber units based in Italy, southern France, and the Balkans had initially achieved significant success against Allied shipping during the North Africa campaign and early Italian operations. He-111 and Ju-88 formations attacked Allied convoys and invasion beaches, with tactics refined through years of combat experience, accepting moderate casualties as the price of successful strikes against high-value targets. The introduction of proximity fuses to Mediterranean theatre in mid-1943 transformed this equation almost overnight. British and American warships, covering the Sicily invasion in July 1943, carried significant quantities of proximity-fused ammunition, with devastating effect on German bomber formations attempting to strike at the invasion fleet. Luftwaffe units reported unprecedented casualties, with entire squadrons decimated during single missions against targets that should have been vulnerable. The pattern repeated during the Salerno landings in September 1943 and again at Anzio in January 1944, with German bombers suffering losses that made continued operations unsupportable. The destruction of Luftwaffe bomber capabilities in the Mediterranean had strategic consequences extending far beyond the immediate tactical situation. German forces defending Italy relied on air support to compensate for Allied advantages in artillery and naval gunfire, but the systematic destruction of bomber units by proximity-fused anti-aircraft fire eliminated this support. Allied ground forces, advancing up the Italian peninsula, benefited enormously from air superiority that proximity fuses had helped establish, facing German defenders who could not call upon effective airstrikes against Allied positions or supply lines. The same pattern played out across every theatre where proximity-fused anti-aircraft defences were deployed, with German military effectiveness diminished not just by direct losses to proximity fuses, but by the broader impact on Luftwaffe capabilities and morale. Bomber crews who survived missions against proximity fuse defences returned to base with reports that convinced other crews their missions were suicidal, creating a psychological crisis that German military discipline could not entirely overcome. The war's final year saw proximity fuse technology achieve levels of sophistication that would have seemed impossible when development began in 1940. Engineers at the Applied Physics Laboratory developed improved fuse models with enhanced sensitivity, better discrimination against false targets like sea spray or rain, and more reliable detonation mechanisms. The Mark 53 fuse, introduced in late 1944, incorporated advances in miniaturization that reduced size and weight while improving performance. The Mark 58 fuse, which entered production in early 1945, featured dual-frequency operation that made jamming nearly impossible and provided better performance against small, fast-moving targets. These later-generation fuses represented incremental improvements over the original design, but each increment translated into saved lives and protected ships when multiplied across millions of rounds fired. The continuous improvement in proximity fuse technology demonstrated American commitment to maintaining technological superiority through relentless refinement, never allowing initial success to breed complacency. The proximity fuse's influence on post-war military technology proved as significant as its wartime impact. The principles established by the VT Fuse program, that weapons could incorporate onboard intelligence to make autonomous decisions about when to function, became foundational to modern smart munitions. The proximity fuse demonstrated that miniaturized electronics could survive extreme physical environments while performing complex sensing and decision tasks, validating concepts that would eventually lead to guided missiles, smart bombs, and autonomous weapon systems. The manufacturing techniques developed for proximity fuse mass production established quality control and testing protocols that influenced post-war electronics industries far beyond military applications. The collaborative model that linked university research laboratories with private industry and military requirements, pioneered by the Proximity Fuse program, became the template for subsequent American military technology development throughout the Cold War and beyond. The human dimension of proximity fuse success extended beyond statistics about shells fired and aircraft destroyed, to encompass the sailors and soldiers who benefited from technology that gave them realistic chances of survival against aerial attack. Every Allied sailor who survived the war, partly because proximity-focused anti-aircraft fire destroyed bombers before they could strike his ship, represented validation of the billion-dollar investment in Fuze development. The thousands of American, British, and other Allied servicemen who returned home to families and peacetime lives because proximity fuses had protected their ships or bomber formations, provided the ultimate measure of the technology's worth. The German and Italian aircrew who died when proximity-fuzzed shells destroyed their aircraft were casualties of a technological revolution. Their nations lacked the industrial capacity to match, victims of a war where industrial superiority proved as decisive as battlefield courage. The strategic bombing offensive's success in destroying German war production and breaking civilian morale owed much to proximity. Fuses that helped bomber formations survive through defended airspace that would have been impenetrable using conventional defensive armament. The invasion of Europe succeeded partly because Luftwaffe bomber forces that might have devastated landing beaches had been destroyed in part by proximity-focused anti-aircraft fire during the preceding years of attrition. The Battle of the Atlantic was won not by any single technology, but by the cumulative effect of multiple Allied advantages, among which proximity fuses ranked high for their role in eliminating German maritime air reconnaissance. Each of these strategic successes traced connections, direct or indirect, to the electronic shell that could think for itself and know when to explode. The Luftwaffe's final dissolution in the war's closing months represented the culmination of technological, numerical, and material disadvantages that had accumulated over years of attrition. Proximity fuzzes contributed to this defeat by accelerating the destruction of bomber forces that Germany could not replace, and by forcing the Luftwaffe into defensive postures where its remaining aircraft fought at increasing disadvantage. The German military's inability to develop comparable technology, despite understanding its principles and recognizing its importance, illustrated fundamental weaknesses in Nazi Germany's approach to industrial warfare. The Third Reich had achieved early successes through tactical innovation and operational excellence, but lacked the industrial depth and organizational coherence to compete in the kind of technological warfare that proximity fuses represented. The defeat of Luftwaffe bomber formations by proximity-focused anti-aircraft fire demonstrated that in modern industrial warfare, victory belonged to nations that could innovate, manufacture, and deploy superior technology at scale. Proximity fuses' triumph over Luftwaffe bombers validated the American conviction that technological solutions could overcome military challenges that might otherwise require unacceptable casualties. The electronic fuse that survived 20,000 times gravity, operated reliably in extreme temperatures, sensed targets through radio waves, and detonated at precisely calculated moments embodied American strengths in scientific research, industrial manufacturing, and systems integration. Its success against German bombers, like its parallel success against Japanese kamikaze aircraft, proved that in the crucible of total war, advanced technology wielded by industrial powers could defeat determined enemies who relied on courage and tactical skill alone. The mathematical precision of proximity, fuse effectiveness, the 3- to 4-fold improvement over conventional ammunition, translated across millions of engagements into strategic advantages that helped determine the war's outcome. The electronic brain in each shell nose, thinking for 30 seconds before making its final decision, represented human intelligence amplified through technology, achieving results that human gunners alone could never accomplish. This marriage of human purpose with technological capability defined American military power in the 20th century and established principles that continue shaping warfare in the 21st. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.